Chapter 4, Counting Methods, starting with 4.1. And I'm going to rename this lesson Counting with Or versus And. First example, how many ways can you draw a black face card or an ace? And we're assuming, of course, this is a regular deck of cards. There's 52, no omissions, no additions. And if we remember what we learned in Chapter 3, the previous chapter, we know a deck of cards is half black and half red. There are 4 aces, so if I want to draw a black face card or an ace, well, how many black face cards are there? That's a face card, that's a face card, that's a face card. And if they're black, we're going to call those spades, or we could call it clubs. So I could draw, there's 6 choices to draw a card from the deck, but I could also have an ace. And I'm not going to waste time here with colors and clubs and everything. You know there's 4 aces in a deck. So I can have one of those or one of those. And I'm just going to take this number as 6, that number is 4, and we can just add those together. The number of black face cards or the number of aces would just be 6 and 4 is 10. And the reason we can just add them together is because these are disjoint or mutually exclusive sets. Okay, and again, I could have a Venn diagram like last chapter. We would do something like that. Okay, and again, disjoint or mutually exclusive again means I can't have a black face card that's also an ace. It doesn't make any sense. How about how many ways can you draw a black card? Any might have been a better word there. How many ways can you draw any black card? Or an ace. Okay, well, we know there's 26 black cards, and B is 26 aces. We know, again, there's 4 aces. So can I just say the answer is 26 plus 4 equals 30? And again, if you took away some information, some knowledge from Chapter 3, you're going to say, no, you can't do that. And the reason why is because these are not disjoint sets. It is possible to have a black card that is also an ace. Okay? And in Venn diagrams, there's some overlap here. We know that there's 2 black aces. And there's also 2 red aces. So actually, if I'm going to do this properly like last chapter, I would have to put that outside. Okay, black cards, there's 26. So in here, black cards that are not aces, then there'd be 24. I have an ace of spades here, I have an ace of clubs here, and I have 2 aces in here that are not black aces. So if I was to count all this up, that's 24, there's 2, and there's 2, and that's 28, not 30. And a little refresher as a formula, that would be the union of aces or black cards. That's the number of black cards and the number of aces, but I have to subtract this intersection here. Okay, the ones that are black and aces. Okay, so that's, again, a little review. That's the OR stuff. Now we're going to look at really what this chapter is about, this AND word here. So, the example. What are the number of ways to have a, I'm going to write too fast, turkey, ham, or tuna sandwich on white or brown bread. Now, I wrote this actually not in a very good way, because I just finished saying I'm looking at this word and I don't see the word and anywhere in this sentence. I see an or there and I see an or here, so it is kind of confusing. I just know in your book these questions, they would put the word and. If I were to reword this sentence, what are your choices to have a turkey, ham, and tuna sandwich on white and brown bread? That's how the questions are going to be in your book. But that's really weird, because I know if you went to a deli and you asked the man, hey, Joe, how many different types of breads do you have? We have white or brown. He's not going to say white and brown. Okay, so that's the confusing part. What's supposed to happen and what actually happens in the real world are two different things. So now we have a choice of meat. I'm going to call those meats. You can argue whether tuna is a meat or not. I don't care. And then I got a choice of breads. So our previous chapter we looked at Venn diagrams. Don't write this down, but so what am I going to do? I'm going to go meat and I'm going to go bread. Okay, and there's an overlap here. What does that mean? A meaty bread, a bready meat, doesn't really make any sense. Okay, turkey, ham, tuna, and I can have turkey on white or brown, but I still have an intersection. How can I have a white brown bread? Don't argue, you can have one slice of each. We're not going there. All right, so what could work is if I go, there's a meat, here's a meat, ham, here's a meat, tuna, okay, and each one of these I could have in white or brown. All right, it's just, yeah, there's ways. Okay, what's the other way I could do it? I could just have, get rid of meat, just white, just brown, and I could have turkey, ham, tuna in each one. Okay, looks like TV. And okay, that looks like it works. And how many choices do I have? Looks like I have 6 choices. We're actually not going to do Venn diagrams anymore, and you'll be thankful, because some of the numbers we're going to see are going to be really, really big, and we don't want to be doing a billion little circles. What's an easier way to do this? Okay, this is you. You have a choice of turkey, you have a choice of ham, or and a choice of tuna. From there, you can have brown, or you can have a white turkey, you can have a brown ham or a white ham, or you could have a brown tuna or a white tuna. This is how we're going to do it. This is called a tree diagram, okay, because it looks like branches of the tree, and you can do it like that and it'll look like prime factorization that you did in grade 10. Okay, it's not wrong to go horizontally or vertically. I chose to move from left to right, but clearly we can see there's 6 choices, or 6 ways to order a sandwich from this particular deli. Okay, so no Venn diagram, we're going to do trees instead. And that one's pretty small numbers. A lot of us can kind of do that in our head, and that's great. But we're going to get ones that are going to be pretty big. All right. Coralie celebrates her 100% midterm with midterm score with an ice cream. What better reward, huh? She can have a choice of 27 flavors. Okay, what's Baskin and Robbins? Is that 27? I can't remember. I think there's one over on the North Shore now. So if I stop there, I think it's pretty clear to all that she has 27 choices to get her ice cream, right? B. She then is offered a choice of, well, this is my favorite, the waffle cone. Or some people, they don't want a cone. Their concerns about whether it's sanitary or not, depending if the person who just handled the cash handles their ice cream cone. So they get it in a cup. Or they could just get a regular cone. So clearly, there's 3 choices here. Okay, I know there's 4 lines, but that's the same line. Continued. 3 choices for how she's going to have that ice cream delivered. So how do I do this with a diagram? Well, I would do my 3 choices here for a waffle, a cup, or regular cone. And if I get a waffle, then what? Well, this is going to get confusing, but there's 27 flavors I could get of my waffle. There's also 27 flavors if I got a cup, and there's 27 flavors if I got the regular cone. So I could have 27 and 27 and 27. There's 81 different choices there. All right. C. Now, hopefully she has a big appetite, because she can get 2 scoops. So now let's do a tree with that. Right, this was 81 choices. So waffle, cone, regular, 27, 27. Okay, 27. I'm being kind of lazy, but I hope you realize why. I'm going to do that 27 times. That's just 1 scoop. Now she's going to get a second scoop. How many different flavors of choices does she have with the second scoop? Well, our problems can get a little more confusing later on, but we're going to assume that she can get the same flavor twice. Okay, so after she gets her 27 choices, each one of these lines has another 27. Okay, obviously we wouldn't ever want to do this with a Venn diagram. I don't even want to do this with a tree. Okay, so I think we're at the point where we're going to need a little formula, but maybe some of us here have come to the conclusion that if I go 3 times 27, that gives me 81. What's going to happen here? 3 times 27, and each one of these 27 choices again has another 27 choices. Put that in your calculator. Yeah, that's a lot of little lines I don't really want to write. It's amazing, eh? Just a simple ice cream cone, and you have 2,187 choices of how you could get that cone. I just want to add this for now, D. She now decides she wants 2 different flavors. Well, how does that affect things? Well, without doing my diagram again, she still has a choice of how to get that in a waffle, a cup, or a regular. She has 27 choices for her first scoop, but now a different flavor means I can't get the same flavor twice. So whatever choice I had, I can't have 27 here. I can only have 26, because if that was chocolate, I could have every other flavor except chocolate. Essentially, it's just one less. Okay, hopefully that makes sense. If I subtract a 27 3 times, that's going to be 81 less flavors, or if I go 3 times 27 times 26, I now get 2,106 ways I could get that ice cream. Or sorry, Coralie could get that ice cream. 2,106 choices. And yes, that's 81 choices less than this. Okay? But enough with big, long, hairy trees. Let's get our fundamental counting principle formula. The fundamental counting principle says if one task can be done A, as in some number, ways, okay? So for example, 3 ways to get a cone or a cup, and terrible writing, and another B ways, etc. Because it doesn't just end with 2 letters, I could do this an infinite amount of times, right? So etc. means C ways, D ways, what have you. But I don't want to write here for a long time. Then both tasks, or 3 tasks, or 4 tasks, etc., can be performed A times B ways. Choices. Okay, if I have 3 choices, and then I have 27 choices, and then I have 26 choices, the total number of ways or choices is A times B times C. Ways. Okay, that is the fundamental counting principle. And it applies again with this word and. Okay? Let me emphasize that again. She's getting an ice cream, 27 different flavors, and she could get a waffle, cup, and cone, and if she's getting a second scoop, she could get another 27. Or 26, depending on the wording, if she doesn't want the same flavor twice. Alright, so a little bit of review. We've looked at ors, now we're looking at this and word, and using the fundamental counting principle. Here's the questions. Can I make this any bigger? Page 235, number 2, 3, 5, 7, 9, 11 to 13, 15, 16, and 20. Looks like a lot, but you know, if once you get the hang of it, they'll go pretty quick.